Hi, I'm Randall Heyman, a mathematics academic. During the coronavirus outbreak, I'm making quick turnaround free videos for educators and students affected by the virus outbreak. So if you'd like me to make a video for you, you can comment below any of my videos, or you can drop me an email. You can see the email address there. So today I'm doing something for Gabriella, who wrote to me about a problem like this problem. It's similar, it's not exactly the same, but it's a similar sort of problem. How do we work this out? I would encourage you, if you're interested in this, to have a look at my video, Modular Exponentiation Made Easy, where I go through 3 different methods to do it, to do these sort of problems. Now, why do these problems come up? Well, I mean, they're used in a whole range of uses, but why do you get this sort of problem in an exam or test? Well, by making it, in this case, 3 to the power of 2018, which we have here, you can't work that out on a calculator unless you've got a very, very big calculator. Because, I mean, that's what you could do otherwise. You just go 3 to the power of 2018, divide by 7, get the remainder, and that's the answer. So it's deliberately designed so that you can't do that. So a lot of people have problems. So I'm just going to go a bit slowly at this point. So the key thing is that we want to reduce, this power, but by reducing this power, we're going to make this bigger, and this will get too big for a calculator at some point. But there's a beautiful trick with modular arithmetic, which is sort of pretty obvious, I think, when you think about it, but people have trouble using it. And that is, well, it was explained to me this way by one of my lecturers at university. When you see this modulo 7, what you do is you go and you go to your maths cupboard and you put on your mod 7 glasses. And these mod 7 glasses, there's a little 7 here actually, which tells you it's the mod 7 one, not the mod 5 one or 4 one. Now the mod 7 glasses have an interesting characteristic, and that is if in the distance or on your whiteboard or on your sheet of paper, you see the number, say, 16. Well, when you look through the glasses, you don't see 16. You see the remainder when you divide by 7. So you see 2, because 16 equals 2 times 7, which is 14, plus 2. So let's do another one. What happens if in these glasses, on the whiteboard, you had the number 703? Well, when you look through the glasses, you would see the remainder when you divide 703 by 7, and that would be 3. Okay? So that's the trick we're going to use. It enables you to make the numbers smaller, and if you can keep making the numbers smaller, eventually the problem will solve itself. Okay. So Gabriella was interested in the computer method, which is quite well suited to programming on a computer. It's quite a regimented method. So if you're a software engineer or something like that, this might be of interest to you. Okay. The first thing that we do, which seems completely separate to what we're doing, is that we need to divide the power here, 2018, into a sum of powers of 2. And you can see I've already done that here. There's only one way to do this if you don't repeat powers. You can see here I've got a 10, a 9, an 8, a 7, a 6, a 5. We missed the 4, 3, 2, and I've just got 1. Okay. Hopefully I've worked it out correctly, otherwise everything else is going to be wrong. Now, so what does that tell us? Well, I'm just going to put here working modulo, so I don't have to keep writing modulo 7 or mod 7. So working modulo 7, we have, what do we have? Well, 3 to the 2018 is congruent to or equivalent, depending on how you want to do this. 3 to the power of 2 to the 10 plus 2 to the 9 plus 2 to the 8 plus 2 to the 7 plus 2 to the 6 plus 2 to the 5 plus 2 to the 1. Now, in modular arithmetic, most rules that you're used to work. Addition works, multiplication, subtraction. Division is problematic. Don't divide unless you know exactly what you're doing. But for this, we can use one of the rules that you learned at high school, which is if you've got, a to the power of x plus y, that just equals ax times ay. So I'm just going to do the same thing here. This is exactly the sort of situation here, where instead of x and y, we've got 2 to the 10 plus 2 to the 9, dot, 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 plus 2 to the 1. So this is equivalent to 3 to the power of 2 to the 10, which is actually, maybe I should write this at this point now, I could write down it's 1024 plus 3 to the power of 512. Oh, sorry, times. That's the point I was making. We have to multiply. 3 to the power of 256. So that's 10, 9, 8. 2 to the 7 is 128. 2 to the 6 is 64. 2 to the 5 is 32. And then 2 to the 1 is 2. Okay. So I'm going a little bit roundabout. Once you get used to what I'm doing, you can do this in a little bit easier way. Okay. So now what we have to do is over here, let's start working out some things. We know what's 3 squared. 3 squared, this is all modulo 7. So 3 squared is 9, but 9 is the same as 2 modulo 7. Remember you've got your 7, or your modulo 7 glasses on. So when you see this 9, you actually, through the glasses, you see 2. Okay. So what's 3 to the 4? 3 to the 32. Well, let's do 3 to the 4. Now, I know that 3 squared, that's 3 squared. Well, that's just the same. We've just worked out 3 squared. Now, you could write 9, but why? Write 2. 2 squared, which is equal to 4. But what's 4? 4 modulo 7 is just 4. Okay, so that's good. Now, 3 to the 8. Well, that's going to be 3 to the 3/4 squared, which is 3 to the 4 we've got back here is 4. That's 4 squared, which is 16. But 16 is the same modulo 7 as 2. Yeah, 14 plus 2, so 2. So 3 to the 16. You can almost see a pattern now. 2 here, 2, 4, 2. If you think about it, what's happening is it's going in this cycle, when this is well understood by mathematicians. If you do higher level maths, you'll see what this is all about. This is not surprising. So 3 to the 16 is going to equal 2 squared, just this one here squared, which is equal to 4. 3 to the 32 is 2. 3 to the 64 is 4. 3 to the 128 is 2. 3 to the 512 is 4. And the last one is 3 to the 1024, which is 2. So looking at this line, I've now worked out what I need to work out. So let's start writing stuff in. So 3 to the 1024, that's a huge number to work out on a calculator, but I can just put 2 because I just worked it out. There, 2. So it's 2. What's 512? Well, that's 4. What's 3 to the 256? Oh, hold on. We've done that wrong, haven't we? 128. I've skipped a line there. Okay. So we'll patch this up now. Let's patch this up. I skipped one. And that can happen. So 3, let's write down here, 3 to the 256 equals 4. And down here I'll write 3 to the 512 equals 2. And up here I'll write 3 to the 1024 is 4. Okay. Now this is all just scrappy stuff I'm doing on the side. You wouldn't need to actually, well, I suppose it is good to explain what you're trying to do. So 3 to the 1024 is 4. See this one here, I'm just reading it off here, 4. That's the beauty of it. Instead of trying to work out 3 to the 1024, I know it's 4. and this one will be 2, this one will be 4, this one here will be 2, this one will be 4, this one will be 2, and 3 squared is 9, which is 2. Okay. So at this point, we can start working things out. What's this? 8 times 8. That's the 8. That's the next 8. That's another 8. 8 times 2. Now, what's 8? When I look through, remember this, the glasses? Here's 8. And what do I see when I've got my mod 7 glasses on? 1. So it's 1 by 1 by 1 by 2. So the answer's 2. So there you go. So that's the computer method. Worked pretty well here. There's also the human method, which is a little bit more flexible. So if you're interested in that, let me know, and I'm happy to go through that to show you. I think I'll leave it there. If you've got any, as I said at the start, if you've got any questions at all about any aspect of mathematics, contact me, and if I think I can help you, I will do so.